I'm going to show you how to simulate a projectile. I'm going to show you how to set initial conditions. Okay, and for this we need to write a script. I'm going to show you output, how to get the data to a Excel or a CSV file. In this case, I'll do a CSV file, and then I'll show you how to read the data in Matlab. Okay, so we'll we'll do a picture of the well, a plot of the projectile motion. I'll also show you how to generate a movie file with CoppeliaSim. It's really easy. After that, I'll show you how to get the position and velocity during simulation. So this is basically showing it in the command window of CoppeliaSim. Then I will add drag force to the projectile like we did it for the Euler-Lagrange equations. And then I'll show you how exactly all these commands you see there in red for CoppeliaSim are obtained through the CoppeliaSim API. And I'm going to show you where that is. It's basically on the internet. It's also in the help, but that is something very handy, and I recommend you bookmark that page so that you can refer to it as and when needed. Okay, so that was the overview which I forgot. So start off, let's say add primitive shape. So if you're doing it with me, this is what you want to do. Click on add primitive shape and then click on sphere, and then you can give some size, let's say zero point 0.1. This is the radius of the or maybe the diameter of the sphere. I think it's the diameter. Okay, and then you see a sphere. uh, if you want to change the color, you can double click on the sphere and then you can change the color. So just color, this is not important. If you don't want to do it, don't do it. um, Whatever you want. Red. Yeah, okay, so that's fine. Okay, now if you, so once you generate an object, um, you can run it by just clicking on play. And not unsurprisingly, it doesn't move because you did not really, well, it's actually moving, it's spinning, but you really did not put in initial conditions, so it's not, you don't expect it to do anything crazy. So what we can do is, if you want it to be dropped like you would drop, say, something under gravity, we'll move it up because now it's resting on the floor, and then see if it drops like it would drop in gravity. So there is this icon here, which is basically translation. Okay, so click on that. So once you click on that, something like this opens up. You can translate it using your mouse. In this case, it's set on mouse translation. um, and you can see then X and Y is clicked. So if you now click on it, you can move it in the X, Y direction, but it'll not move in the Z direction. If you want to move it in the Z direction, we unclick all but Z, and now move it up. Okay, and then if you want to see how it works, just it drops like to under gravity. Okay, now it doesn't quite look realistic, so that's just running a forward simulation and then showing you how it works. If you want to show it, what will happen when you drop it actually in, also to say, have the frames depict real world, then real life, then you just to toggle on the real time mode and then drop it. So now it drops slightly more realistically. Okay, stop. Okay, so that's basically mouse translation, and I would encourage you to explore these options, which is basically you can set the position using X, Y, Z, uh, and some other ways. Okay, I just stick to these two usually. Okay, everybody who's working on their computer on the same page, did you get it to bounce off? Question, let's see what the question is. Can you obtain numerical output data z dot versus time, for example, for plotting outside CoppeliaSim? Absolutely, you can get that. And I'm going to show you how to do that. Okay, what I forgot to show you, and I should have shown this much before, is okay, so we're back. So, okay, so we've got the projectile to drop. Now the next step is, can we launch the projectile at a certain speed, okay, which is more interesting than just dropping it down. So let's first go ahead and save this. So save scene as, okay, let's save this as projectile. And then it takes care of the extension, which is TTT. Okay, it's saved. Okay, so now what we do is, the way we set up initial condition is through a script. Okay, so I'm going to show you how to create a script associated with the sphere and then write code to launch the sphere with a certain speed. So for that, I click on scripts on the left side, if you can see my screen. Uh, Actually, there's a lot of things here. You can actually get rid of this whole icon, this whole tab by clicking on, let's see, not this one. If you click on this, the robot kind of thing, it gets rid of that. So you don't need that in this particular case. So just got rid of that. So again, press scripts and something like this opens up. Now we'll say insert new script. Okay. And then you see there are a bunch of options. Okay. So the you can read about what scripts do, but the main script is default. It's something which you should not edit, and if you're an expert user, you will probably edit it. But then there's other things which actually are the ones which will be used in this course. One is the child script non-threaded and child script threaded. The difference is that the non-threaded script is something like what it'll do is it'll do the computations and then pass control to something else and come back. It will not really execute things real time. But a threaded script is more for a real time operation where it just won't wait for something to complete the computation. You just keep running just like it would in real life. So you probably want to do things in non-threaded fashion when you want to just develop your code. Once you have optimized it and it's ready to go on the robot, you want to probably try it out as a threaded script, which basically tests if the script can run quickly enough for it to be executed on the robot. Okay, now customizing script, I'll skip. Let's choose it to be a non-threaded script which is not real time, and say okay. There's a bug here, which is you should be able to associate with the sphere, but it doesn't really work. So once you select this and it's come unassociated, just close this window and then reopen the script. And now when you click on non-threaded script, you can tell it, you can associate it with what object. In this case, it really doesn't matter. You can associate with anything, but let's just associate with the sphere. Okay, so we've associated with the sphere. Okay, anybody not got here or wants me to show something again, let me know. Okay, I'll just assume we've all on the same page. Okay, let's move on. So this by itself doesn't do much. It just associates a script. You can double click on the script and you'll see that it has this code inside it. The initialization is, so these are function calls, okay, just like your functions in Matlab. The initialization function is called the first time the script is executed. So if you want to initialize some parameters, that's what you do it. If you want to actuate, like if you have motors or you want to add forces, like in this case we'll add drag forces, you want to put it here. If you have sensors, in this case there are proximity sensors, vision sensors, you'll add that code here. And then finally there's some cleanup code, which is basically before you exit, you want to clear some memory, you write code over here. Okay, so this is basically the framework and we'll basically populate these items here. Okay, now, okay, so if you search for CoppeliaSim API, then you should see something like this. I'm going to share the link, which I think I did. Okay, I would recommend, highly recommend that you bookmark this page. So it's an easy reference. Okay, so first thing we want to do is find the handle, object handle, object, object, object handle. Okay, so you can see that there is sim dot get object handle. I click on that, and then what I need to do is there's actually synopsis in C and then there's Lua synopsis. I'm going to use the Lua one. So I need to basically look at this particular command, okay, and then sort of use it for my purposes. So it basically gives you what exactly is this particular function in Lua. We'll copy this. I'm going to paste it here, and the reason I paste it in the init is because when I initialize, I need this thing to get the handle. So if I uh, then get put the object, in this case it's the sphere, then I need to give it a name. Okay, I can call it whatever I want. You can call it sphere handle. Say, okay, doesn't really matter. So if I do this, and if I just say print sphere, this is just printing what the output of this particular function does. Actually, you'll see. So I'm going to close this. This is where things get printed. I'm going to run it. And then you can see there's a number 83. That means that the way this object is understood or interpreted in CoppeliaSim is by a number, which here in this case 83. And you saw that it's printed 83 just once. That's because the init is called once. Now, if I do the same thing slightly differently, I just take this and paste it in the actuation part of the code, okay? And now run it. And you can see it's printing 83, 83 all the time. That's because the part actuation is run every simulation loop. Okay, so that's a very important distinction between the init and the actuation part of the code. Okay, so I'm going to paste this here. I don't quite need it. So once we've set the sphere, we got the handle for the sphere. Now our job is to set the initial velocity. Okay, and the way initial velocity is set is again in the API. So there is something called float property. Float parameter. Set object float parameter. Okay, now the question is, how did I even figure out it? You can set the initial velocity using set object float parameter. The way I did this was actually, I did not know how to do this. I actually Google searched in for this particular thing. How do you set initial condition? And then I went to the CoppeliaSim forum, and that's where somebody hinted out that you use float parameter, and that's how I learned about this function, and that's how I'm able to use it. Okay, so it's not, sometimes it's, you don't know how what exists in CoppeliaSim, but you have to just search for them. So in this case, if you search for object float parameters, it turns out that the name for this, or the call for this, is going to be something like this: set object float parameter object handle, and that object handle is basically, in this case, sphere, the parameter ID. Okay, we don't know what a parameter ID is, but the number parameter, this is basically giving the value for the parameter. So we need to find what is the parameter ID for initial speed. So for that, let's look at list of all possible object parameter identifiers. Okay, and then there are a bunch of them. Okay, so here we want to search for velocity. This is the object absolute x velocity. This is okay. This is not the initial velocity though, it's just a different velocity. Uh, joint velocity. There's no joint here, so we can skip that. Joint upper limit. Lock. Okay, it's probably here. So it says init velocity x, initial dynamic linear velocity, and that's what we want. We want to set the x velocity, the y velocity, or the z velocity. Now there are two ways to do this. You can either specify the parameter to be 3000, or you can give it this name. I'll show you both ways. So let me open a new tab, go back here, copy this line. Okay, and since the velocity is set once, I set it in the init function call. So set object float parameter, object handle. The object in this case is the sphere. Don't call it by this because that's not how CoppeliaSim recognizes the sphere. Number parameter ID. Okay, so let's go to here, and there are two ways of really setting the velocity. Velocity. Okay, I think it's 3000. Okay, okay, so one is you could put 3000. Let's go here and set it to 3000. And then this is basically, I forgot to do this. Um, it says x velocity. You know what? Let's just set the y. If I set the x velocity to a high value, it will just go zooming past in the right side. Let me just set the z velocity, which is upwards. Let me put 3002 first, and then I'll change it, put the x and y. So 3002, and let's set it to, so right now it's 0, right? Because it's just falling down. Let's set it to some positive value, let's say 10. Okay, and now let's see if we are able to get what we want. So it see jumped in the, sprung in the air, and it fell down. Seems a little bit too much. Let's reduce it to maybe 2. Yeah, there it is. So it went up before it went down. So I said the other way to do this is to actually call it using this. So let's set this up instead. This is an easier way of remembering. Instead of remembering 3002, you can just remember this, which is much easier. So let's just change that. So I'm going to make a copy of this. Okay, and comment this. Comments in Lua have 2 icons. And I hope it runs. Let's see. Okay, it worked too. So these two things produce the same output. Okay, I'm going to put this in the chat. So if you are running this with me, you can run it. Okay, now let's do the same thing for x and y. Okay, in fact, let's say x and then say y. Now what we'll do is, to make our life easy, we will only launch the projectile in the xz plane. We'll not launch in the y plane, because then it becomes it's easier to visualize in the xz plane in a single plane. So let's just set this to 0. Let's set the x velocity to a small value, and then let's just make it this maybe 5 or something. Okay, now let's see what happens. So you can see it dropped, and stop this. I'm going to zoom out. So if, for a Mac, I think scroll the I use 2 fingers and scroll down to get it to zoom out. Okay, there should be a similar thing for Windows. Okay, now we can run this. You can see it goes, and then it'll actually fall down because the floor ends there. It'll stop. Okay, so that is setting up an initial velocity. Now let's go to the next part, which is, can we graph the position as a function of time? For that, what I need to do is I need to create a new object called graph. So just like I did a sphere, I say add, I say graph. To add, I said graph, and then you see graph appearing. On the right side, you see how you want the graph to be. So for example, you want it to be visible when simulation not running or running, you can set that here. What is the preferred position? I like to keep it on the bottom left corner, so that way it doesn't intrude with the animation. Okay, so that's just getting the graph. Now we need to tell it to plot the, say, the x and z as a function of time. So what you need to do is double click on graph. Once you double click, you see something like this. Here you can add a new data stream to record. So let's click on that. And so here we want to set, in this case, see, simulation time. That's going to be our x-axis.
Dr. Bonso, where did you click again?
Okay, so I double click on graph.
Oh, that graph, got it.
And then I said add new data stream. And then here I can call it time. So again, let's do it for X. So add new data stream. Here we want the absolute X position. And then it asks you want the absolute X position for what? So in this case, the only object which is moving is sphere. So let's click sphere. And you see something like this. In this case, I selected the time X position. I'll add a new data stream. I'll call that Z position, and then associate with the sphere. Okay, and call that Z position. Okay, now let's just run this. And you can see that on the left side, you see this all are red lines. And one of them, in fact, is, well, one case I was plotting time versus time, which makes no sense, right? So I'm just going to delete that. So if you want to delete something, just double click again, graph, click on time, and then just say delete, and it takes care of that. Now, even if I have two things in red, it doesn't help. So what I'm going to do is I'm going to change the color of one of them. So let's take the Z position, click on Z, say adjust curve color, and then you can change that to, let's say, blue. So now let's run this, and you can see the blue line and then the red line for the X. Okay, let's stop this. Okay, so that's basically showing you the X and Z versus time. Occasionally you might want to do something different, like in this case you might want to plot the Z versus X, which is showing the projectile trajectory of the height versus the distance traveled. So in that case, what you can do is click on graph, uh, say edit XY graphs, something like this opens up. Let's add a new curve. The X value is going to be X position, the Y value is going to be the Z position, and say OK, close, close. And then here we want to see the XY graph now. So I'm just going to click XY graph and run this. So you can now see that the projectile is showing the characteristic parabolic profile, and then it eventually falls down. Okay, so that's how you get the XY graph. Okay, now next thing is, how can you output this data to somewhere else? Let's say you want to publish this or visualize this in Matlab. In that case, what you need to do is, after you run the simulation, all you do is you say file, export selected graphs as CSV. So just click on that. And then it asks you, where do you want to save it? So I'm going to save it someplace. And we call that projectile plots. So that's saved. It is basically saved in over here, projectile plots. Let's open that up. Okay, so once you double click, it opens up like this. Here you can see that it basically gives you the legend, and then the X, the time position, the time, the X position, the Z position as an array. Okay, now, well, once you have an Excel, you can use Excel to plot it, but I like to plot it in Matlab. So let's open Matlab. Okay, I'm waiting for Matlab to open. So now let's do the same thing, CLC, clear all. If you want, close all. Okay, so now in this case, I want to read this file, and it's called projectile underscore plot. So the way you read files in Excel as CSV files is this command called read table, and you say projectile plots.csv. Okay, let's save it in the same place where we saved the other file, so it can read it. Projectile plots. Let's say read projectile. Okay, now if I run this, okay, it's done running. It actually, you can actually check what data is. So data is basically the output. Uh, if you double click that, it actually gives you the output in Excel, which is open inside Matlab. Okay, so it actually gives you the time, the x position, z position, and really you just want the data. You don't want these x time, x position, z position, and time seconds, the legend essentially. So I close that. So there's a way in which you can tell Matlab to only read the data and not read the first, in this case, the first two lines, right? So what you do is, uh, and this is something which you can search by doing help read table. You say header lines 2, which means that you're telling Matlab that the first two lines are the header lines. Uh, are the header lines, and so you can ignore them. So now if you run this, it'll actually produce, I don't know if you can see it, but data. Let's see what happens here. Okay, didn't quite make the point that it doesn't read that. But if you try to take this t equals data 1 x z, and then if you do figure, I'm going to answer the question on the chat in just a bit. Plot t x, say subplot 311. Okay, that just creates three plots as an array of 3 by 1, z and x, z. Okay, so let's just run this, and then it produces a figure on the other screen, which I'm just showing you here. This is basically the x, xt, zt, and zx. Now zx doesn't quite look like projectile because it actually fell down into the ground, right? Okay, so if you skip header lines, say that you just skip it. Okay, and you run this, it actually gives you an error. It gives you there's a problem. It actually does generate the plots though, so it warns you that uh, it actually has, it got sort of confused with this t and x because you also include the header lines, but you can use it either way. Okay, so that's how you take this data from CoppeliaSim into CSV and then written Matlab. Now, there was a question. If you can get simulation data in real time with Matlab, is Matlab capable of real time? Isn't that more of the, okay. So the two parts to it. One is, can you run CoppeliaSim and start controlling CoppeliaSim from Matlab? So if you can do that, then you can actually get data from CoppeliaSim, perhaps in whatever speed at which CoppeliaSim is giving data, and then use it. It turns out there is a way to do it. It's actually called, there is something called remote API. So Coppelia remote API. Okay, so the remote API, there are two frameworks. This is the legacy one, and then there's the new one. But the way this goes is, Coppelia is a server, and then your application, which can be C, C++, Python, Java, Matlab, Octave, Lua, are clients, and they can actually talk with CoppeliaSim. So you run a code from Matlab, talk with CoppeliaSim, and CoppeliaSim starts sending in data. So that is like, that is how you can emulate you can make Matlab talk with CoppeliaSim. Uh, can you make it real time? Actually, yes, you can make it real time, in which case you will need to use a threaded script. So it's the threaded script basically ensures that what you're running is real time. So you can use Matlab. You don't have to be restricted. Simulink is just another way of writing Matlab code. Matlab is the line based part, and Simulink is the the graphical one, but I think they're practically the same in terms of functionality. You can get the same features in MATLAB as you get from Simulink. So you can actually run this like you can actually run MATLAB code and talk with CoppeliaSim, and that's something which I've planned. I'll actually show you how to do that, how to write MATLAB code to talk with CoppeliaSim and get data. It's just something which is slightly more advanced, and I want you to be more comfortable with Lua first before we get that. Because some of the scripts, even if you write MATLAB code, it turns out that you need to be able to write Lua scripts to get MATLAB to work for certain commands, and that's why you want to be more comfortable with Lua before you go to MATLAB. Okay, so it's certainly possible. Okay, so let's close this. Now, the next part was we've already seen how to uh, create a simulation and get the data. Can we make a movie file? Turns out that's super easy. Okay, so this is how it's done. What you need to do is you need to open the video recorder. Okay, in there you can say launch the next simulation start, and then there are a bunch of formats in which you can get the data. Now I've tried a few of them. The one which works for me on my machine is this one. Maybe something else works for you, and you can play with it. So you can say that, and then you say the location. I'm going to put the same location trying to do the movie recording. So as I said, you go to uh, let's see. So I basically say launch at next simulation start. I choose where I want to record it, which is CoppeliaSim 401. And then I choose the last option, which works for me. And then I say play the simulation. The pause dropped, and then I stop before it falls down. This is where the recording is generated. This is the folder where it was generated. Same file. Right, 35. Okay, and let's open it. This is what shows up. Yeah, so you can actually get it so it only records this part and not the left part. I think you just replay the settings. But yeah, so it's a useful thing to have, which is to be able to record easily, right? Okay, so that's about recording. Last time I was, you can see my screen. Last time I was doing this projectile motion, and the projectile falls and it just rolls off. The I pretty much set uh, the initial velocity in the x y z direction, and that's why it sort of uh, shot in the air and then fell down. Okay, the next stuff is how do you actually get the position and velocity of the ball as it is executing its motion, and if you have that you can perhaps write it to a file. This is other than doing it from the graph, right? The graph actually gives you the output. So again, as I said, you need to have the API with you. So I have saved the link to the API, and I'm going to search for object position. So position. So you can see this is something to do with the joint. I'll skip that. Joint. They're still in joints. Set path doesn't look like what we want. This here. Get object position. Looks like this is what we want. So let's click that. So you see that this is the Lua synopsis. So I'm going to copy that. Go to my code and let me do it this way. So we can write the code and also see what's happening on the screen. Okay, and then zoom in a little bit. Okay, perfect. Now let's put this here because we are calling it an actuation because we want to read the data at every instant. So I copy pasted that. So this just says that the output is going to be a table. A table is very much like an array for Lua. It's basically going to give the position, in this case x, y, z. Okay, then it says get object number object handle. So the object handle in this case is going to be sphere. I need to maybe reduce this further. It's easier this way. Okay, so let's change this to sphere, and then it says relative to object handle. Let's see what that means. If you go back over here and see what relative object handle is, it means that it's the relative to which the reference frame we want to the position. Specify -1 to retrieve the absolute position. So which means that if you want it with respect to the world frame, you need to put -1. So I'm going to put -1. And now that I got the position, I want to print it to the output screen, which is right here. So what I'm going to do is, first of all, move this up. Then I'll go here and then say print position 1. So the indices start from 1 for Lua, just like in Matlab. Position 2, position 3. Okay. And now what I can do is I can go here and run this. So you can see that it's printing something now. If you stop this and if you scroll up, see where it starts from. It starts from well, so I think I started it from -1.0. Okay, let's see if that's the actual position. I'm going to stop this, kill this. Oh my god, this is a, I need to, you can't stop it, quite stop it here. Okay, now stop it. I think this position was actually the one which is shown here, which is -0.1, 0.124 and 0.8. So you can actually check this by clicking on position, and then this opens up. And if you look at a position world, it's actually -0.1, which it is -0.1, 0.125, 0.125, and 0.8. 0.8. So that's pretty much what is over here. Okay. So that looks right. And then it just keeps printing that. Okay, so that's the position. How do you get the velocities? Let's search for velocity in here. So velocity. So since it's here sim get velocity, that looks like what I want. So I'm going to open that and then see what it is. This table, linear velocity, table, angular velocity, sim.get velocity, number, shape, handle. So I can just copy, paste this in my code. So this is again saying that I need to get the position, sorry, the velocity is the linear one, angular velocity, and I need to give the object handle. So that's going to be sphere. Okay, so now I just need to print the position, or the velocity, sorry. So I'll just go with this linear, and I can also print the angular velocity, but that doesn't seem to be very interesting here. So I'm going to stop, comment that out, and then let's run this. And let's stop, and let's go up and see what the velocity was. So simulation started 0, 0, 0, 0, 0, 4.5. That's interesting. I expected it to be, I believe I set the velocity to be, let's see, if you set it over here, right here, you set it to 1, 0, and 5. So the x velocity is 1, y is 0, and z is 5. And what am I seeing here? 104.5. I guess this is missing a few frames. You can also get it in the first time step here. This is the initialization, and so maybe now it will be more consistent. Okay, stop. So if you go up, it's saying 1. Is this right? Yeah. So it's 0, 0, 0. It's apparently, I think it's 0 over here, but then it's not clear to me why it would be 4.5. It should be 5. Okay. I don't see any problem with this code. The x velocity is right, y velocity is 0, and the z velocity, instead of being 5, it's 4.5. It looks like it's missing a frame. We can actually also get the simulation time to verify this. So let's get the simulation time. Simulation, or let me just search for time. So get simulation time. So we can just pick it from here. And that's relatively simple. So let me comment this out. And let's get the simulation time right here. We call that just time. It should be called sim dot get simulation time. And then I can print the time also in addition to that. So I think this is a user, since showing it in orange, it means that it's probably defined within Lua. It'll give an error. Let me just call it time, capital T. That way it's unique to our code. So let's just run this now. Hit stop. And let's go back and see where so 0, 0, 0, 0, 0.05. So that's the time. That's the x velocity, the y velocity, and z velocity. So what you can see here is that it's actually missing time t equals 0. It's not really printing the velocity at time t equals 0. It's printing at 0.05. So that's the velocity it is after 50 milliseconds. So I guess it's okay. It's sort of right. Okay, so that's how you get the position velocity, and then once you have that, you can use it to do whatever you want. So in this case, what I'm going to do is I'm going to add a drag force. And the drag force depends on the velocity, right? So that's why I got the velocity. So let's set up the drag force. So remember that the formula for drag was something like minus c times vx times square root of vx square plus vy square plus vz square. That's for the x in x direction, and then you can do the similar thing for the y and z. So let's just first figure out the forces in the x, y, z direction. So let's define a constant c equals, say, 1. Vx is, we know it is simply the first component. Then we have the y, which is the second component. Then we have the z, which is the third component. Then v magnitude is going to be vx times vx plus, I think you can actually write it as vx squared instead of writing vx times vx plus vy squared plus vz squared. And then if you want to do the square root, it turns out that the square root is, you can't just write sqrt like you would in Matlab. I think, maybe it works. Okay, let's just keep it that way and see what happens. So that's the square root, and then what we need to do is then define fx equals minus c times vx times v, fy equals minus c times vy times v, fc equals minus c times vz times v. Okay, now the question is, how do you add this drag force to the object? It turns out that there is a way to do this. by a function called add force torque. So if you search for force, okay, skip all this, we go to the top of the page. Okay, let's search for force. Okay, seam rate force, max force, add force. Okay, so these are the two things which are of interest. Add force, let's look at add force. So adds a non-central force to a shape that is dynamically enabled. Okay, so what that means is central forces are forces which act at the center of mass. This one adds a non-central force. So if you look at the way this command is it basically says the shape handle, and then you need to give the position, and I believe the position is with respect to the center of mass, and then you give the force. Okay, that's one way. The other way to do it, and which I think is the much simpler way, you could add force, but I'm going to use the other one, which is add force torque. Okay, the good thing about force torque is that it adds a force at the center of mass, and that's what we want. And in this case, you specify actually the force at the center of mass, and also a torque if you need it. So if there's no torque, you just put 0. So we just copy this, and then go to our file, and then paste it. And by the way, one thing I forgot to say is that this force and torque are force and torques about the absolute x, absolute y, absolute z. Okay, they are not about the body frame. Okay, so if the body is spinning about an axis, then its axis will change, and that's not going to be the force applied along those axes. In this case, we actually want it to be about the world frame. If you want to apply a force with respect to the body frame, then you will have to first find the transformation from world frame to the body frame, and then use the transformation to transform the force from world frame to body frame. And this is something which we will do a little bit later when we talk about the Jacobians and so on, but let's skip that for now. So let's use this. I'm going to put sphere, and then I need to give force, which should be a table, and then torque should be a table. So let's just give the force. So force is a table, so it's going to be force, fx, fy, fz, and then torque is going to be 0, 0, 0. Okay, so this applies the force. Let's see what happens to the simulation. Okay, so there is a problem. What's the problem? Attempt to call global SQRT. So SQRT is not available within Lua. So it turns out that if you want to invoke SQRT, it's in a math library. So you need to say math.sqrt. I'm pretty sure it'll work now. Okay, so you can see that it actually stopped right there. It didn't quite move after it fell off on the floor. Okay, that's because the drag force is a little bit too much. Let's just make it 0.5. Okay, and then play it. So it's now slightly rolling. Okay, we can change that a little bit lower. So that rolls. Okay, that's it. So that's pretty much about how to simulate a projectile with drag and save the data and do graphs. Okay, any questions? Can you change the step size? Yeah, of course, you can change the step size. So I forgot to tell you about this. So then there's this whole thing about how do you run the simulator. Now, when you did ODE 4.5, for some of the questions, you defined the tolerance. That's basically tells you how accurate the integration is. In here, there are actually, just like ODE 4.5, there are these various engines used to compute the integration. Okay, Bullet is perhaps the more accurate one, other ones are slightly less accurate. You have the choice of doing a simulation fast, or you can do it more accurate. So usually you want to stick to accurate. And then the last point is the step size. Now, when you use ODE 4.5, ODE 4.5 is an adaptive integrator, which means that it will not have a constant step size. It will sometimes use a small step size, a big step size, so as to integrate, and that it does based on some error tolerances which it has inbuilt. So that's why it's called ODE 4.5. It's a fourth order method with a fifth order correction. Okay. Uh, Bullet here, on the other hand, is a fixed order integrator, which means that it's like what is known as ODE4 or Runge Kutta 4, which means that it basically integrates with a fixed step size. So in this case, the step size is chosen to be 50 milliseconds, which is clearly less accurate than using, say, 25 or 10 milliseconds, which is smaller. So let's try 10 and then run this. It doesn't look like it had a big difference. It's very similar. So if you want to check how the how accurate is the simulator, then you can actually well, you can change the time step, but the best way to check how accurate the simulator is, if there are no dissipative forces, you want to look at the total energy, kinetic and potential, and if that's constant when there's no drag force, of course, then the integration is accurate.